What's up, guys? I have a very crude, unfinished, um, some graphical models of the universe or some universal components. So let's start with how can gravity be explained through expansion and contraction? Okay, so let's go ahead and start with four objects. Um, these four objects start kind of far apart, as you can see, and we want them to get closer together. Well, what happens if we lock their position and just make them bigger? So we can see that this top one is a little bit bigger than those bottom ones, but they're all perfectly lined up. They're just getting bigger and bigger. Okay, so each frame they're getting bigger, but they're not moving at all. Okay, so hopefully you can kind of see it on this angle. They're not moving, but they're getting bigger and bigger and bigger and bigger and bigger, and then eventually they collide because they're getting bigger together. And you can see that I have not moved them closer together at all. They're still on an absolute value. They're still right in the exact same spot as they were. But somehow, if you were sitting on the cube and you were getting bigger with the cube, then you would appear to be just moving towards these blocks. You'd have to imagine these frames running in your head. But the expansion of something is hard to explain on a universal level. Where does all the energy come from for something to expand? Is there a way that we can create this out of collapsing? And it turns out that there is. Go upstairs, I'm making a video. I can't pause it. It's bad enough I gotta yell at you on the video. Please, go. Okay. So if we zoom out, I'm going to start with four cubes, and I'm going to call these cubes, they're just going to be objects, but they're going to be local objects. They're going to be existent inside of a galaxy, not outside of a galaxy. So these are like planets, suns, and you and I. We are all part of this local expansion. And so what we're going to do is, these things are moving toward each other at a certain rate. Okay? But they're also shrinking. So at each iteration down, it does not really look as if you've moved at all. This here is called a USO, a universal scalable object. Okay, so we're going to zoom in farther. We're going to see that these objects are getting closer and closer together, even though they're shrinking to infinity. They shrink forever to infinity following the phi curve, and they continue shrinking following the phi curve to their shrinking, and eventually you get to the spot where oh, I zoomed in on the wrong one. Oh no, okay, it keeps going. So it's running into the box, the reference box. That's why I got rid of it. But if you keep going, they keep shrinking and they get tinier and tinier and tinier. But as they're getting tinier, they're also getting closer together because they're falling toward each other inside of a giant black hole. Okay, which gives us this. So you can see the reason I showed you this first. You can see that you can do a whole set of mathematics with expansion, and then out of all the infinite possibilities of all the rates that I could have chosen for the shrinking and for the falling towards each other aspect of this, for any of those, an infinite sets of different rates, these things will converge together, and you can do the exact same math through contraction, so space contracting. So instead of looking at this, because this is actually a very crude example, and I haven't had it drawn properly, but I did show what a galaxies are. So this is our, well, this one holds proportion, that one holds proportion. So this is more like our galaxies, okay? Let's go over here and I'll show you an example of the objects being, galaxies being pulled towards each other without shrinking. Okay, so they're just, and I don't have this, I just literally am stepping in 1 unit every time. So it's not how the actual universe is, it's just a graphical model to show a property of the universe. And so I have it over here. You can see this is the path of motion that everything takes. Everything comes together and meets in the center. Like this. And so that's coming together without shrinking. This one here is an example of shrinking but not coming together. So you can see this literally just shrinks into infinity, and if we go down here, we are so far away from our counterparts. It's that little blue thing there, which I doubt you can see. You can see that in this example, everything is expanding away from each other. Okay? Everything is expanding away from each other. So this is what the galaxy does. All these galaxies are expanding away from each other because the entire galaxy is shrinking at a certain rate, and it's not necessarily constant across the board. And so I'll show you an example of some of these rates. This is a linear rate showing that these galaxies are falling apart. So simply imagine, just for keepsakes, imagine right now, and this is not how the example should actually be told, but to get it to follow through and to understand it as humans, just imagine this block as a black hole. It's not a black hole. There's not a black hole in the center of this. We are talking about all of these objects being inside of a black hole. We cannot see the edges of the black hole in this example, but we can see the center, or there is no center of this black hole, but we can see the central point of our example, which is this blue piece that I've clicked on. And so now each iteration, because we're inside of a black hole, we're going to be getting smaller and smaller and smaller and smaller with each frame, okay? And now we're also getting closer and closer and closer and closer. So you can see that these galaxies are moving toward each other. If I zoom out like this, you can see that these galaxies were here, and now they're here, and now they're here, and they're slowly stepping in. Boom, 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 boom. They're stepping into the center, moving toward each other. However, they're moving toward each other at too slow of a rate. And as these things shrink farther and farther and farther, they're shrinking so quickly that as they look at their counterpart galaxies, as they look out at them, they see them moving away. Look how far away that is over there. That's way over there. Look how far away that is over there. It's huge. As they keep going down farther and farther and farther, these things just keep going farther and farther and farther away. So we're standing on the edge of our galaxy, and we're overlooking to find the other one, and we can barely see it. The cube covers it, the giant center cube, so it's right there. So it's getting really, really, really far away with each and every frame. And that's exactly what we witness here on this planet. When we look out with our telescopes, we see the galaxies going very, very, very far away. So they're not following this curve. This is a linear distribution that I put through here, and it's just moving in one absolute unit at a time. So it's actually the inverse square and the square law that applies to all of this. And in some cases, it's to the power of the fourth, over the power squared, which ends up with a square anyways. But so these things fall together much faster. If I drew this model 10 times as big, I would only be able to make it 4 frames before the show is over. Not even 4 probably. And so I've actually already tried drawing a bigger one with different curves. So to draw this accurately, you would be shrinking these and putting them to closer together at some rates that are natural to our universe that we witness, and then they would cancel each other out and create another rate that would have to match up to what we witness the galaxies physically doing. Now, because you're in a black hole, the space around you is infinite, okay? Because a black hole is an infinitely small point, and if you are inside of it, then the space around you is infinite. And all these galaxies are infinite as well. Now, they don't have a perfectly uniform structure like I'm showing you here. They have different galaxy type densities throughout the universe, and that kind of affects the central point of this expansion slash contraction factor that we've just checked out. The central point, and so when we look out, we can find what we see as the center of the galaxy, or not the center of the galaxy, but the center of our universe. And what we can see is that the center of the universe is actually just the center of the dominant expansion. Everything else is expanding equally around us, except not equally because of the different densities that exist. And so these different densities change how much an object can move relatively in its environment. And so really heavy galaxies are not going to expand, or contract away from smaller galaxies as fast as a smaller galaxy contracting, or a big galaxy contracting away from a big galaxy. Okay, it's a tongue twister, but the different densities of the different regions of space affect the amount of shrinking or contracting that's actually happening in that region of space. And so we actually have to stop the video, and I have to make another video taking off from here.